I'm going to be measuring the Sinewave's 3 parameters using DSP Speedster. Here's the sine wave generator. It's being contaminated by Gaussian white noise additively, and I'm able to control that mixture by setting my signal to noise ratio. The measurement block for this is this one out here, which is a DFS spectral interpolation meter. And just to have a look to see what's inside of it, it's a very high quality algorithm. This is the references in here. Malcolm McLeod's algorithm, 1998, transaction signal processing. There's a reference to it. FFT based algorithm. And if I push in to see a bit of more detail, I see of course a fairly busy sort of algorithm, but I do see that there are 3 selections taking place, and those are the peak, the DFT point, which is the peak, and also the 2 adjoining ones, and the rest of this is interpolation. And when I go back out to the higher level, I can see that I pipe all the way out here with a frequency estimate. Similar sort of blocks in here. You can see the complexity is not all that great. You can follow through it without too much trouble, and that's easy to write directly from the paper, and that then gives us a phase and also an amplitude estimate. So this should do a good job, and we expect that. So as we run it, what we see is a pretty stable frequency estimate, amplitude jumping around a little bit, phase jumping horribly all over the place. Maybe it's to do with noise. Let me crank up the signal noise ratio up to 100 so that effectively I got a noise-free situation. I look back over here, I'm a bit bemused to see that in fact the frequency is stable as it is, but phase jumping around just like it was before now in a noise-free case, and even the amplitude not completely steady. Makes me wonder, first off, first question is, what is the true answer? So I click on the sine wave here and I see that I've got a 1.23, which yeah, could be the case. The 56 degrees phase, well, I could never deduce that from these measurements right here. Quite happy with the fact that I've got frequency within about 1/10 of a hertz pretty solidly. So what is going on here? I need to think about this a little bit more, and an aid to my thinking is of course to instrument a bit. Let me go reach over to Speedster and get myself a signal analyzer, hook it up to my noise-free sine wave, run it and see what's going on. Well, a nice stable sine wave, shouldn't be any big problem, but I've still got these measurements jumping around. So what is going on? I need to think a little bit further. I need to bring in my labmanship skills a little bit here. So let me think like this algorithm. This algorithm is taking 1024 points in, is being presented with that. So instead of these 300 points here, it's more fair to change the buffer size in this signal analyzer to 1024, so that it really is viewing the very same thing the algorithm is. When I run it now, I see lots of oscillations, but I don't see this stability. I see that the thing is jumping along, and is, in fact, as the buffer load by buffer load, I see that I do have effectively a random phase coming in. So probably this is working just about right. So I might think. If I want to be a little bit more persuaded about this, let me shut the model off, keep it in its noise-free situation more or less, and think about a different choice of this frequency. Maybe a magic choice which would exactly fit in without all this randomness of phase. Well, I can do that. Suppose I wanted to have 10 oscillations taking place within that frame of 1024 points. Well, I happen to know that the sample frequency is 20 kilohertz, and you need that in this calculation. Take the sample frequency divided by the buffer size of 1024, and it turns out to be 195.3125. Well, let me swipe that number right there and put that in to my signal generator's frequency, and move the decimal point over so I don't have to type all this stuff. And now I've changed it just a little bit. I'm keeping these phase and frequency values. I run again, and now I see a nice stable display. The algorithm's presented with that, and lo and behold, here's my amplitude smack on the new frequency, which I now have, and the 56. Well, let me just change something here just for kicks. I'll change this back here to minus something, minus 91 point something, change the amplitude to something else, and it's quite okay. But of course, this is a noise-free situation. What happens when I go back to noisy? Well, let's crank it down here and see now. Those are very, very stable results so far. But of course, noise starts disturbing this thing when I get down here about 10 dB or so. Of course, we see what the algorithm is presented with, and I crank it on down further, and I can see that I'm still getting a pretty, even at minus dB, I'm getting a pretty solid frequency estimate, and my phase is beginning to jump, but nowhere near as badly as it was before, because of course I had the advantage of coming in here with this very, very magic frequency choice. Even so, noise exacts its toll, and nothing is perfect.